Thank you, Andrew, for the introduction, and good morning, everyone. It is a pleasure to be here. I first, wanted to thank Andrew for organizing this symposium and giving me the opportunity to contribute to it. My talk will essentially be about comparing how different markers of functional connectivity encode behavioral information. So before defining the different markers of functional connectivity that we will be using, I wanted to recall the definition of functional connectivity, which is a statistical dependence between different time series. And so when you are dealing with this data set, so with functional data, that typically looks like this and consists of different time series that reflect more or less directly the level of neuronal activity in different regions of the brain, you have different ways of computing functional connectivity because statistical dependencies can be computed in many different ways. So the classical way of computing this statistical dependence is to use the correlation. And if you compute the correlation from this data set, this is what you get. You end up with a matrix that is supposed to encode all the functional connectivity information that is contained in your data. And here, this matrix encodes for each pair of brain regions a correlation between these regions. But let's now think what we assume in terms of generative model when we have this static representation of functional connectivity. Well, what we implicitly assume is that fMRI time series are generated by a multivariate Gaussian model that has a mean 0 and a covariance C, C being the covariance or the correlation matrix that you compute from your fMRI time series. So this is the generative model of fMRI time series that you assume when you use a static approach, a static representation of fMRI time series. And if you generate data from this model, this null model, and then apply a sliding window correlation on it, this is what you get, where the blue curves represent the time courses of correlation between different pairs of regions of interest, and the red curve is the average between the blue curves. So this is typically the type of properties that you are able to generate and to produce when you have a static approach. And if we compare this to the properties that we observe in real data, well, we see that definitely we are missing something. There are some statistical properties included in real fMRI time series that we are missing if we limit ourselves to a static representation of functional connectivity. So let's now see how the autoregressive model does. So if you have, instead of a static generative model of fMRI time series, an autoregressive model, we assume that each fMRI time point can be represented as a linear combination of the previous time points. And here I will be focusing on a first order autoregressive model, which means that each time point depends only on the previous time point. And here, dynamics is used in a different sense than the classical dynamics that we have, so it might be a bit counterintuitive. Usually we think of dynamics in terms of time-resolved information, as Andrew mentioned previously. Here, dynamics refers to the fact that we are exploiting the memory of the system. And this is a definition that comes from the engineering community, from systems theory literature, so that's not a definition that we made up. And we will see that exploiting this memory of the system, it's something that can be very powerful. Because if we now generate data from this generative model, this is what we get, and we now see that having this model of fMRI time series allows to capture the dynamical properties, the time-varying properties of the correlation that we observe when we use a sliding window approach. And hence, from a statistical point of view, an autoregressive model is capturing much more information as compared to only a correlation matrix. So the two markers of functional connectivity that we will be using are this matrix C, which is the correlation matrix of the data that will be the static representation of functional connectivity, and the model parameter A of the autoregressive model identified from the data. These two matrices have the same size. These are square matrices of size which is equal to the number of regions of interest. Okay, so what we've been doing here and what I've highlighted here is the fact that from a statistical point of view, we are capturing more information if we use an autoregressive model and a dynamic approach. But then I would say regardless of the approach that we are using, if we are using HMM or whatever other model, the next step, the next question is to see whether it allows to extract useful information from the data. Because in the end, if you are just modeling better the statistical properties, but we are not extracting any useful information from the data, that's pointless to go for more complex models. So that's the question we asked next, which was to know whether this additional statistical information that we have when we use a dynamic representation of functional connectivity also carries behaviorally meaningful information. And to explore this, we use the HCP dataset, the latest release of the HCP dataset, and we end up considering 917 subjects. We used all the runs that we had for all the subjects. We did a minimal pre-processing and global signal regression. We then parcellated the data into 400 regions using the parcellation mentioned here. And the two markers that we will be using to characterize functional connectivity are the ones mentioned in the previous slide. Then to link these markers of FC to behavioral measures, we use a heritability model. So we will be linking the functional connectivity markers to 58 behavioral measures that are also available from the HCP dataset. We regress these parameters from the behavioral measures, and the statistical tests that I will present were done using the delete one jackknife method. So let's now spend some time briefly on the model that we use to link functional connectivity markers and the 58 behavioral measures. So we use the model developed by Tian Ge and collaborators in 2016 that has already been used in these types of applications, and that writes as follows. As follows, where on the left, Y represents the behavioral information, and F is a subject-specific information that is computed from the functional connectivity markers, and E is residual noise. So essentially what we do here is to see the extent to which behavioral information can be explained by functional connectivity measures and metrics. So going a bit into the math here, Y is a vector of size n, and F is also a vector that is generated from a multivariate Gaussian distribution with a covariance pattern that is driven by this functional similarity matrix F. So how do we build this functional similarity matrix? Well, each entry of this matrix tells us how similar the functional connectivity patterns of two subjects are. And so to compute this, we simply use the correlation between vectorized versions of the functional connectivity pattern of subject I and subject J for the entry, the corresponding entry. And then we end up with a with this quantity of interest, which encodes the amount of inter-subject behavioral variability that can be that is encoded in that can be explained by inter-subject variability of functional connectivity patterns. So we do this using, as I said, static and dynamic markers of functional connectivity, and this is what we get when we apply this to all the subjects. And we see that on average, dynamic functional connectivity explains much more behavioral information than static functional connectivity. So on the right, I also represent some of the 58 behavioral measures, which are here the cognitive measures. And this is the first interesting result because it means that using a dynamic approach, we first encode more statistical information, but this statistical information translates into more behavioral information. But then we also wanted to question whether this behavioral information is located and generated by connectivity patterns in more specific resting state networks, so by the connectivity patterns within these networks. And so to question this, we use an adapted version of the functional similarity matrix that is now computed from a comparison, a similarity between the connectivity measures within specific networks. So for example, if we focus on the DMN, we will use only the connectivity measures within that network, or within another network, the visual network, or considering the connectivity between two networks. So here the DMN and the visual network. And if we do this, this is what we get. And these results were a bit surprising because we show that in this case, static information seems to capture more behavioral information than dynamic functional connectivity. And so that means that DFC, when computed at the whole brain level, is capturing more behavioral information because it's able to capture the interaction between multiple networks. This can also have an interpretation in terms of integration, segregation, where DFC would be more related to integration between different networks, and static functional connectivity would be more capturing segregated properties of the brain. And then finally, the last analysis we did is to explore whether static and dynamic functional connectivity markers are capturing different types of behavioral information. And to question this, we compared behavioral variance explained by SFC and DFC, but for each behavioral measure. So we end up with the t-statistics for each behavioral measure, and we then order all the measures based on these statistics. So this is what we get, and on the left we have the measures that are better explained by static functional connectivity, and on the right we have measures that are better explained by dynamic functional connectivity. And if we now label the different measures as follows, so in red we have the self-reported measures, which are the measures for which we have asked the subjects, for example, to evaluate his feeling of loneliness or the quality of his social connections. And in green, we have labeled all the measures that correspond to performance in a task, such as working memory tasks or math tasks, etc. And we see that there seems to be a dichotomy that is drawn based on these t-statistics. And we show that task performance measures are better explained by dynamic functional connectivity, whereas the self-reported measures are explained equally well by SFC and DFC. So this means that the advantage of DFC at the whole brain level seems to be driven by its capacity to better explain task performance measures. So a first reading of this would be that the brain needs to be more dynamic when the subject is doing a task, but this opens, I think, new avenues for the interpretation of functional connectivity and how this can be used to understand different behavioral properties. So with this, I would like to conclude and first say that, in my opinion, the autoregressive model, even if it's a single model, so that has constant parameters in time, is a very promising model to capture these dynamics that we've been discussing a lot now, but in previous sessions and previous editions of HBM also. The other points relate to the results that I presented. So the fact that DFC at the whole brain seems to capture more behavioral information, which is not observed when we focus on specific resting state networks. And the last result that I just presented in terms of this dichotomy that DFC and SFC seem to draw within behavioral measures. So with this, I would like to thank the collaborators on this project, and in particular, Thomas's team here at the National University of Singapore, and I thank you for your attention.